Hello everyone and welcome to my video. In this video we will talk about the convergence in the sense of distributions. And before we actually start with the content of the video, I would like to thank you about the support and warmth you always show towards my channel. And this is my first video in English, so I hope you will appreciate it. And I would like to remember you that you can support my activity here on YouTube, clicking in the like button and subscribing to my channel. You can also show support towards me in a more material way, because I will leave the links to my Ko-Fi and my PayPal in the description below. And that's all. I can start with the actual content of the video. So as I have anticipated, we will talk about the convergence in the distributional sense. So basically, in this kind of exercises, we have a sequence of functions which are basically real function of real variable, which also show an explicit dependence on an integer index. Obviously n belongs to the natural numbers, and what we will do is basically to consider the linear functional associated with this sequence of function t of n, and we will also consider the pairing of this linear functional with a test function phi. And then, since the exercise is actually asking us to check the convergence, we will then consider the limit for n which tend to infinity, and then we will have to calculate to which specific distribution this sequence of functions actually converges to. So this is the main idea of the problem, and for those of you that actually have to study distribution theory, this is actually a very common exercise to study. So let's consider our function. We have this function, we have f n of x, which is e raised to minus x minus n, again raised to the power 2. So we have x minus n squared, and we will have to consider the linear functional associated with this sequence of functions. We will denote it with t of n, and this is a little terminological note that I want to highlight, because I see with a lot of students that they do not have very clear the concept of linear functional. So basically a linear functional is an object, a linear object, that takes input, takes functions as input and gives real numbers as output. But we need to represent this kind of operator, and the most natural way to represent it is basically via an integral. No, we have this integral extended to the whole real line of this sequence of functions. Okay, and then we have to input something here, and then we have to integrate obviously in dx. Naturally, the input it's not chosen randomly, but we chose functions from the space of test functions. So phi in general belongs to the space of test functions D, and this is what a linear functional actually is. Is an operator which takes functions as input and gives back real numbers. Obviously, since we are in distribution theory, function again are not chosen randomly, but we choose this function from the space of test functions. So only to recall to our viewer what a test function actually is a function with compact support, so it is null outside of this support. outside of a closed interval or region, if you are in r raised to the nth power, and they are also infinitely differentiable. This is what a test function is. So basically are the most well-behaved function you can think of. So after this theoretical premise, we can go on with our exercise. So we want to check to which distribution this sequence of functions actually converges to. So we have to consider the linear functional, so we have to consider the pairing between this sequence of function and a test function. And so let's do things in order. We have to consider limit for n which tends to plus infinity of t of n which acts on phi, and then we have to consider the pairing. This more explicitly can be written as limit for n which tends to plus infinity of the integral extended to the whole real line of f of n x phi of x in the x. And again, okay, this is an equal sign. We can make this function explicit since they are giving us this function in the text of the exercise. And we have limit for n which tends to plus infinity of e raised to minus x minus n raised to the power of 2, and then we have a generic test function extended to the whole real line. And then the most convenient way to continue this exercise is basically to expand this square here, and we have to consider limit for n which tends to infinity of the integral extended to the whole real line of e raised to x squared minus 2nx plus n squared, and then we have phi, and then the whole thing is integrated in the x. Okay, then we observe in this exponential that actually only these two terms actually depends on the independent variable x. So we have what it's basically a term which is constant with respect to the integration. So we can pull it out the integral, and we can write limit for n which tends to plus infinity of e raised to minus n squared, and then we have the integral. We have integral extended to the whole real line of e raised to minus x squared minus 2nx, and then we have a whole parenthesis, and then we have our test function in the x. Okay, and then to make things clearer, we can write limit for n which tends to plus infinity of this is e raised to minus n squared, so we can write it as a ratio, and obviously the denominator will be e raised to n squared, and then we have our integral here. We have e minus x squared minus 2nx phi of x in the x. And so now that we have written our equation in this way, we are in a position in which we can infer to which values each component of the ratio will tend to. So in the numerator we have an integral, and the integrand function is basically a function which is composed by the product between a test function, and we know that test functions are 0 outside of a finite interval, Okay, finite, which is also a closed interval, so this is their definition, and we have that e raised to x squared minus 2nx is a function that tends to 0 pretty fast when x tends to asymptotically large values. So we have this thing that is 0 outside a compact set. We have this function which tends to 0 when x grows asymptotically large, so we can conclude that this integral it's surely something finite. Okay, on the contrary, we have e raised to n squared, and we have n which is tending to an asymptotically large values, and so we have that this element here will grow exponentially large, and so since we have a finite value divided by an element which grows exponentially large, this limit will give us 0, and this irrespectively of the test function we choose. So we can conclude that our sequence of function f of n of x when n tends to plus infinity tends to the identically null distribution, basically to 0, and this in the sense of distributions. So this is our exercise basically. So we have seen this first exercise in the theory of distribution, and as always, I would like to thank you for your attention, and if you want, you can show me support, and thanks for watching, and see you in the next video.